So there's a 300 million year gap between that evidence for cyanobacteria and the evidence for the oxygenation of the atmosphere and hydrosphere, and that's intriguing and is not readily explained. 3 billion years ago, there are stromatolites in South Africa, in what's called the Pongola supergroup, small conical stromatolites that are of a type that in the modern world are also built by cyanobacteria. We can't be sure. We only have the morphology of the stromatolites. There's no supporting evidence, but it's suggestive that there could have been cyanobacteria 3 billion years ago. And even worse, if we look at the microfossils that are now known to be relatively abundant in the older rocks in the Pilbara region here in Western Australia, in rocks that are 3.4 to 3.5 billion years old, there are filamentous microfossils which could be interpreted as cyanobacteria. They needn't be, but they could be. And also in those rocks there are stromatolites, particularly ones with conical laminae, that are most readily interpreted as having been built by cyanobacteria. Now you couldn't call it compelling evidence. It's not compelling evidence that there were cyanobacteria in those earliest times, but it's suggestive. If there really were oxygen-producing, oxygen-releasing cyanobacteria at 3.5 billion years ago, why did it take until 2.4 billion years ago to oxygenate the surface of the Earth? And that's a very good reason for coming here to Shark Bay to look at just how these modern stromatolites are forming.